Okay, hi guys. After that last class, I decided I wanted to try to make a couple of videos on how to solve a calorimetry problem. I know maybe some of you needed a few more times going through it, or just somebody to break it down step by step. And so I created two documents that I have attached to an email that I sent to you. One is called Steps to Tackle a Calorimetry Problem. And the other one is how to invent an original calorimetry problem, which is your assignment for this coming week. I think I said I gave you 2 weeks to get it done, but do not get out this week and then the test the following week. We're not trying to do everything all in the same week. And it's really not that hard. You'll see once I get to the steps and we just work our way through it. It doesn't take too long. I'm hoping to just take a few minutes to get this done. So hang in there with me, and I hope that this helps you out. I'm going to turn on an additional light just so that you don't get this shadow effect on the board. So give me just a second, and I'll try to get that done. Okay, well, we still kind of have a shadow, but hopefully it won't be too bad. And I hope you can see, looks like you can see the board, and so we will just work. This is going to be the steps to tackling a calorimetry problem. There are several in the book. I'm just going to take two of the on your own problems, and we'll just work them through just to make sure you understand what the step process is. If you're not having a problem with this, you don't have to watch the video. But if maybe the math's giving you a little bit of trouble, then I hope that the video helps. Be sure to give me some feedback so I know if it helps or not, and what might have made it a little more helpful. Let me get my book, and I'm going to open it up to the right problem. Okay, so on your page, I hope that you already have gotten this page and you've printed it out, so you can just kind of walk through it with me. Again, this is how I set it up. If you come up with another way and you're getting consistently right answers, feel free to just do it any way you want. I just thought I'm visual, and so this kind of a process helps me. So step number one, create the chart. When I say the chart, this is what I'm talking about. Every calorimetry problem is dealing with three things: the object, the water, and the calorimeter itself, the actual machine that, or the tub of water or whatever that you're going to be dropping things into. So there's three things. So they go across the top on the page. We have the object, the water, and the calorimeter, and I am just going to stop it at calor. Okay, I think you'll understand that. Then there are 6 things that we need to keep track of for each one of these objects. We need to know the Q, the mass, the specific heat capacity, the temperature that it ends, so that's, I'm calling the final temperature, the temperature that it started, okay, the initial temperature, and then what is called the delta T. Okay, and that's the one we need for the equation. Just so you all remember what the equation is, it's Q equals mass times specific heat times the change in the temperature. That can be positive or negative. You're multiplying these three together and you get the answer in joules. So there we go. That's what we need to know for all three objects: the Q, the mass, the specific heat, the ending temperature, the beginning temperature, which we're going to subtract and get the delta T. And we need it for the object, the water, and the calorimeter. Okay? That's kind of maybe disconcerting to some people. We'll try to straighten that up a little bit. How's that? Is that better? Okay. We still have a crooked one in there, but that's just what we get. Okay, so that's step number one. Step number two is to read through the problem and see if you have to count that calorimeter. Remember, many times the calorimeter doesn't absorb enough heat or absorb enough energy that you even have to consider it. Sometimes you can throw this out, and sometimes you have to include it. So read the problem and see if we have to include it. Let's do that. This is on your own problem 2.8, and it says, a calorimeter holds 175 grams of water at an initial temperature of 25.3 degrees Celsius. A 54.3 gram piece of metal at 100 degrees Celsius is dropped into the calorimeter. The final temperature is 27.1. What's the specific heat of the metal? You notice he didn't say anything about the calorimeter at all. He didn't tell you how much it weighed, which we would have to know. He didn't tell you its specific heat. So that is your big clue that you don't need the calorimeter for this problem. So just X that out, okay? Or squiggle it out, however you want to do that. You don't have to count the calorimeter in this one, okay? That's step 2. Just figure out if you need it or not. If you do need it, which you're going to see on the next problem, we'll just fill in that information as we go. But for this one, we don't. So that's step 2. Step number 3 is enter all the information you're given about the object. Okay, so let's read it. Or I guess you could just kind of fill this out as you go through. And it would look something like this. A calorimeter holds 175 grams of water. That is your mass of water. 175, and it is a 0.0 grams of water. My points are difficult to see. There it is. Okay, 175 grams of water at a beginning temperature of 25.3. So of the water, it's going to start at 25.3 degrees Celsius. Now, a 54.3 gram piece of metal, that's our mass of the object, .3 gram piece of metal, we don't know what kind, at 100 degrees is dropped. So it's starting at 100. Okay, 100.0. Let me back this up. Give me some more space. 100.0. So it starts there. Is dropped into the calorimeter, and the final temperature is 27.1. 27.1. And it's the same for both. Degrees Celsius. Trying to keep all of the units going. So it says, what is the specific heat? Let me just make sure I'm keeping up. I've said step 3 is to enter everything you know about the object. Step 4 is to enter everything you know about the water. Step 5 is to calculate this delta T. So let's just do that now, okay? 27.1 minus 100.0. Okay? I know this sounds ridiculous, but let's just go ahead and plug it in. I don't trust myself on any of this. So just, it doesn't hurt to plug it in. And you get 72.9, but it's a negative. Because the negative, you know, minusing 100, because it takes you past 0, right? So we're at negative 72.9. Now, keep in mind, what does the negative mean? That means it's losing heat. Whichever thing is losing heat, is the delta T will be a negative. If the object is hot and then it cools down, it's losing heat, so its change in temperature is a negative. This one, the water is going to be positive because it's adding heat on. Okay, so that is the delta T for the object. And we can, I think we can do this one in our head because it doesn't go past 0 for me. 1 minus 3 is 8 and 1 because this became a 6, right? 1.8. Now don't just make it a negative. It's a positive in this case. It gained a temperature. It started at 25. It ended at 27. Right? So it gained. So that's fine. I circle these. I circle them for me because when I start doing my equations and I look for a temperature, you don't want to enter one of these by accident. You want to enter these. So I circle them so it just reminds me and helps me not to make that mistake. There's one other piece of information we can fill in. We know what the specific heat for water is, 4.184, and it's joules per gram degree centigrade, right? Can you see that? 4.184 is always the one for water. So, on your thing, on your sheet, I say it's common, it's very common for this whole line to be empty. So when I say look for an empty box, I'm not talking necessarily about this one. That's common. But there's one empty box, okay? And I sometimes circle that so I can keep track of, that's what I'm looking for. I'm looking for specific heat. So I'm also looking for a certain unit. I'm looking for joules per grams degree Celsius. So if I do some math problem down here and I end up with grams, I go, wait, that's not what I'm looking for. I'm looking for joules per gram degree Celsius. I'm just saying that because you can help yourself keep track of, am I on the right track or not? So once we have this, now you're just going to use your equation. The Q equals MC delta T, right? And you have to use it for both columns. If you use all three, you have to use Q equals MC delta T for all three columns. Okay, but I'll show you how this works. Right now, I'm going to just erase this. Okay, and the way I do it to help keep it all, let me move this over a little bit like that. Okay, up here at the top, this one I have everything but this. So I'm going to work with water. So I write water. And I put a line there, and I Q equals MC delta T. Kind of looks like cat, but it's not. I don't know Q. That's what I'm calculating. I know mass is 175.0 grams times 4.184 joules per grams degree centigrade times the delta T, 1.8 degrees centigrade. You can see that degrees Celsius goes away, grams go away, leaving us with joules, which is our unit for energy. So we know we're getting the right thing. All we have to do is plug that in. I hope you can read that. I know, it looks a bit confusing right now. That's joules. So we're just going to enter that straight in. 175.0 times 4.184 times 1.8 equals, and we get 13. Wait, that's just dirt. 1317. 1317.96. Okay? Now that's what you get on your calculator. That's what you get on your calculator. Too many significant figures. When you're multiplying, you count the least number of significant figures. Look at that. You can't quite see. There we go. Okay, so 1.8 has only 2 significant figures, so we can only have 2 significant figures here. Okay, which means I can move this decimal. Boom, boom, boom. I moved it 3 times. So I know it's 10 to the third, and it's 1.3. 1.3 times 10 to the third gives you 2 significant figures, joules. Okay? Another way you can do it, once you type this into your calculator, it's going to give you this number. It's going to give you 1,300, which is also 2 significant figures. These two don't count, and don't put a decimal because then you have to count it. So it could be 1,300 joules, whichever one you want to use. This will calculate the same way as this. They're the same number. But let's plug that in. So that's for water. It goes right here. All right. Energy becomes your bridge. This goes directly to here. It's 1,300 joules, but it's a negative number. Okay? It's losing the heat, so it's negative. This one's positive, this one's negative. But it's the same number. Okay? And then once you look at this, now you have everything except for specific heat. Okay? Let's go back the other way. And let's do it for the object. Object. And let's manipulate our formula. I want C by itself, so I'm going to divide by M delta T. Okay? Which makes that go away, that go away. Can you see how that happened? So now I have C equals Q divided by mass times delta T. I'm going to turn it around. Equals mass divided by Q divided by mass delta T. So Q is negative 1,300. Mass is 54.3. And my change in temperature is negative 72.9 degrees Celsius. I hope that makes sense. I just plugged into the equation. No, that's not true. I got it. So I was going to talk about significant figures, but that's it. Now we just need to plug it in. I have to get my calculator. I dropped on the floor. All right. Let's try this. Here we go. Ready? 1,300 negative. It gives me, you can't see it. No. 1,300 divided by left parentheses 54.3 times 72.9 negative in parentheses and then equals. And that gives you, C is 0.328. 0.328. Okay, and we count significant figures. We have 2 there, so we can only have 2. So you can drop the 8, or you can round it to 33 joules per gram degrees Celsius, because everything stays. There's joules, grams, degrees. Okay, and that's what goes right here. 0.33. And that's your answer. Okay, I hope that was easy enough for you on that one. But we need to work just one where we have to include the calorimeter so you can see how these joules work out. So we're going to open our books. We're going to do one more problem, only this time we're going to include the calorimeter. And then we'll be done with this video. Okay, I hope that looks clear enough. Okay, so do you remember what our first step is? Create the chart, right? So again, this is just the way I do it. It kind of helps me keep it straight. And I do tend to get the right answers when I use the chart. So we have the object, the water, and the calorimeter. We need the Q, the mass, the C, the final temperature, the starting temperature, and the delta T. Okay, you see it doesn't take you that long just to kind of make that out. Now we're going to do problem 2.10, okay, in the book on page 60. If you want to look at it while we fill out this chart, okay? The next thing I want to do is find out if I have to include the calorimeter. A calorimetry experiment is performed with a calorimeter that has a specific heat of 3.77. As soon as he tells you what the specific heat is or what the mass is, you're just going to have to include it. So we might as well just start plugging that information in. The calorimeter has a C of 3.77. It has a mass of 9.5 grams. This is joules per gram degree Celsius, right? I think you know that by now. It's filled with 117 grams of an unknown liquid. Uh-oh, so it's not water. We're just going to have to say liquid. It doesn't happen very often, just every now and then when he wants to throw you off. Okay, 117 grams. No decimal points, it's just 117. That's initially at a temperature of 25 degrees Celsius. 25 degrees. 25 degrees Celsius. And the calorimetry has the same. Okay, whatever temperature is the water is also the calorimeter. If a 50-gram chunk of copper at 112 is dropped into the calorimeter, okay, let's just start filling that out. If a 50-gram chunk of copper, 50-gram chunk of copper, and the specific heat for copper, I think, is 0.38. Let's look back, see if we can get that. Copper, 0.38. 0.3851 joules per gram Celsius. Okay, and it starts at 112. It's dropped into the calorimeter, and the temperature increases by 2.3 degrees. It increases by 2.3 degrees. So 2.3 degrees. That's not the ending, okay? You have to add back up to get that. So we get 27.3, right? That's where we started, 27.3. And we get 2.3, but this comes across 27.3, And then we have to minus 112. So let's do that. 27.3 minus 112 equals negative 84.7. Okay, that's its delta t. So this one, and this one is what you'll need for the equation. Let me show you what you're going to find. Okay, I said it's common for the top layer to be empty, but there's just one empty box, and we can say, oh, he wants the specific heat of the liquid. Let's find out if that's what he says. What is the specific heat of the unknown liquid? So we know we're on the right track. Okay, we have to use this energy as our bridge to get to this one. We have to use Q equals MC delta T for all three, basically all three columns. So let's just start working, I guess. Let's start with, I'm trying to see what the easiest place for you to see. Let's start back over here. We're going to say the object Q equals MC delta T. It equals 50 grams times 0.385 joules per gram degree Celsius times negative 84.7. Yeah, I know. It's kind of running together. That's not very easy for you to see. But I think you see where I got all of those numbers. They're right here. 1, 2, 3. We plug them in. We plug them in. It's that simple. 50 times 0.3851 times 84.7 negative equals Q equals 1630. I have three. So we can only have three significant figures. 1, 2, 3. That works. Okay. 1630. There's a negative sign. This would be negative. Okay. That object is losing energy, so its energy has to be a negative sign. We can also work this one because we have the mass, the specific heat, and the delta T. So write down underneath it, let's just say for the calorimeter, I'm wondering if you're going to be able to see this. Q equals MC delta T. It's 9.5 times 3.77 times 2.3. There you have it. And then we plug it in. 9.5 times 3.77 times 2.3 equals 82.37. 82.37. But I only have two significant figures, so this has to go drop back to 2. Or how about if we just drop that and call it that? Q equals 82 joules. Now, here's how we fill this out, okay? You found the joules for the object. You found the joules for the calorimeter. And the other equation is that the energy of the object, negative 1630, equals this one plus this one. So we could call this x plus 82. So what number goes in here? What plus 82 will equal 1630? Forget the negative sign, okay? They're equal in value. The sign just tells you the direction of the heat flow. So 1630 minus 82 equals 1548. Okay, 1548. Let's check it. Plus 82 equals 1630. So now I know these two together make 1630, and that the energy of this object is just the negative of that. So I know this is correct. 1548 joules. And now you see you have everything in the center column to run your equation again. Last time. The only difference in this time through is we're trying to find C. So if I take Q equals MC delta T, and I want C by itself, I'm going to divide by mass, divide by delta T, divide by delta T, and these go away, leaving us with this. C equals Q divided by M delta T. And we just plug in. 1548 divided by 117 times 2.3. 1548 divided by 117 times 2.3. You plug it in. 1548 divided by left parentheses 117 times 2.3 right parentheses equals. You have to always hit that equals at the end. If you just stop after you say 2.3 right, it's just giving you this number. When you hit the equals, it does the division. Okay. And we end up with 5.75. And we have two significant figures, so we're going to say 5.8 joules per gram degree Celsius, which is the specific heat of our unknown liquid. Okay, I hope this helps. And I know it was a little bit tedious, but now you've worked both ways. And if you have your chart and you have those two equations down, then you've got it made. Now I hope you enjoy the other video on how to create your own calorimetry problem. It works kind of the same way. It's just then you have to figure out what you want to tell. So I'll walk you through how I made mine up. Hope you enjoyed this. Hope it helped.